Okay, so you have already seen what is written in the blackboard. So if you look carefully, then you are going to see that it has whatever uh, I left you with yesterday. So if you recall what we were trying to do yesterday, suppose we have a space curve C in some region omega in R3. So then we were trying to construct an integral surface corresponding to a vector V on which that particular curve lies. Is it okay? Fine. And then I had given you a theorem, and that theorem, it was about some integral curves. And then I was telling you procedures while I took two cases where in the first case that given curve it is not an integral curve corresponding to a vector field V. So that means at no point of the given curve the vector V is tangent, and in the second case the given curve itself is an integral curve corresponding to that vector field. So I had simply given you some procedure, but I didn't concretely prove anything about that. Okay, so today what I am going to do, I am going to prove the theorems related to those two cases. The first case being where V is nowhere tangent to the curve C. Okay, and what we did, this I have already told you yesterday. So what we are going to do, this curve C in omega, we are going to parameterize it through this function. We are going to parameterize it through these three functions, x0, y0, z0, and their functions of a single variable t, where t lies in an interval I. And see, this one may sound a bit confusing, because here what we are assuming that the curve C, it passes through the point x0, y0, z0, and whereas for the functions also I am using the same notation x0, y0, z0. Please don't get confused with that. So these are just functions, and of course they are, I mean, C1 function in I. Okay, and what further assumption we did? We assumed that this particular point x0, y0, z0 lying on the curve C, which has been parameterized through this single variable t. So for a fixed value t0 of t belonging to that interval I can get this point. So basically x0 equal to etc. Okay, fine. So then let me look at the theorem. So what does the theorem say is that suppose you have been given a vector V whose components are P, Q, R, and it is defined in that region omega. Okay, and we are given that at the point x0, y0, z0 of the curve C, V is not a tangent. So then, in some neighborhood, omega naught of that point x0, y0, z0, there is a unit integral surface of V containing that part of C in omega naught. See, I am not concerned about the whole, curve C. It is good for me or good for you. That means it is good for us if we can find an integral surface in the neighborhood of that point x0, y0, z0. Okay, so now let us try to prove this theorem. Okay. Okay. So think I'll be needing more. Okay, proof. Okay, fine. So what we are going to do, firstly, we are going to define, like say, let U1 and U2 be two functionally independent, first integers. First integrals of what? V. First integral of V defined say in the neighborhood of say this point. Neighborhood of this point x0, y0, z0. Okay. And what we are going to do, please be careful about it. We are now going to define two functions. We are going to define two functions, say u0 and u2. They are functions of t. Again, they are going to be defined in the neighborhood of this point t0 belonging to this interval I in such a way that your u1 and this is equal to say small u1 okay, and then u2 is small u2 z0 t. Okay, fine. Now let me, I will assure you and then I am going to prove it to you. So what is going to happen? See, we have been given that the vector v is not tangent to the curve C at the point x0, y0, z0. I have a situation like that. Is it okay with everybody? If you look at this figure, I have a situation like that. See, this is my curve, C, and this is the tangent to the curve C at the point x0, y0, z0, and we have assumed that the vector v is not tangent to the curve at the point x0, y0, z0. Fine? Is it okay? Yes? Yes. Okay. So now let me tell you this assumption is going to lead us to the conclusion that I can eliminate t from these two equations. I can eliminate t from these two equations, u1 given by this and u2 given by this. Okay. See, suppose I can eliminate say if I can write t in terms of u1 from this equation. So then I am going to substitute that here for t, and that is going to give me a functional relationship between u1 and u2, right? And that is going to give me eventually the integral surface of v in the neighborhood of the point x0, y0, z0. Okay, so that is what we are going to do. We haven't proved anything here. Okay, so now let me tell you what the procedure is. So now, for that, what we are going to do, we are going to find the derivative of capital U1 and capital U2 at the point T0. And we are going to make some I mean observations from that. Okay, fine. See, your du1 dt at t equal to t1. So obviously, what is going to happen? Again, say u1 is what? Small u1, x naught t, y naught t, z naught t, isn't it? Right? So this is what this is going to be. What this is going to be? Like if I use chain rule, if I use chain rule, what is going to happen? Like x naught t, this is simply what? This is simply what? U eventually being a function of x, y, z. Again, x, y, z themselves are functions of t. So basically, what this is going to give me? This is simply going to give me what? Grade u1, fine, dot. Yeah. It is going to give me what? I mean, this one. Is it okay with everybody? And this will be at t equal to t naught. Is it okay with everybody? Fine. It is simply chain rule. It is simply chain. Okay. Fine. Now, similarly, your du to dt, it is at t equal to t naught. This is also something like grade u1 at x naught, y naught, z naught, and then dot this. So sorry, this is grade u2. So at t equal to t naught. Okay, fine. So now what I'm going to claim that at least one of these two, is non-zero. At least one of these two, either du1 dt or du2 dt at t equal to 0 is non-zero. Okay, so in order to prove that, see, if one of them is non-zero, so then what is going to happen? By what? Implicit function theorem. By implicit function theorem, I will be able to express t in terms of u, and that is going to give me a way to eliminate t from capital U1 and capital U2. Is it okay? Fine. So that is what I am going to do. And in order to achieve that, the very fact that your what? I mean V is nowhere tangent to the curve, or for the time being, I mean here, V is not tangent to the point x0, y0, z0 to the curve C is going to have. Okay, so let me show you how it is going to help in that case. Okay, fine. Now, let me, please remember this. Please remember this. I'll just try to draw a figure. Okay, fine. So before drawing the figure, let me tell you one thing. See, U1 and U2, what are they? They are first integral of V. This is the first information. Okay? And not only they are first integrals, the second information is that they are what? Functionally independent. Right? They are not only Fi, they are also Fi. Yes? Yes. They are not only first integrals of V, but they are also functionally independent. Okay, fine. So that means if I consider this product, at the point x naught y naught z naught, so what is this product? This product is nothing but, if you consider some level surface corresponding to these two expressions. So then this is going to be what? This is going to be a normal to the surface at the point x naught, y naught, z naught, and this one is going to be a normal, right, at the same point to this surface. Is it clear to everybody?
Yes.
Right? So then what is going to happen? This is simply nothing but the cross product of the normals, right, at that point. And we had already developed a theorem earlier, right? When we define integral curves, at that time you saw that what happens, like this cross product, right, being what? Perpendicular to both these normals, right? It is going to be what? It is going to be along the direction of v bar, because u1 and u2 were nothing but the first integrals of v1. Is it okay? You remember that?
Yes.
Right? Here we are assuming that, I mean, v is not tangent to c, right? But whatever happens, if u1 and u2 are two first integrals, not only first integral, I mean functionally independent first integral, so that, I mean, this is not equal to 0 at least at that point, zero vector at least at that point. So then their cross product is going to be along the direction of v bar. Clear? Isn't it?
Yes.
Now, see what is being given. Now, say, suppose I consider this, and again say the figure will go something like this. Y, Z, and let me try to draw it. Okay. Suppose this is your C, right? And then this is the curve x naught, y naught, z naught. Okay, fine. And what I can do, because it corresponds to the point t naught, right? I may call this vector as r prime. This vector as r bar t naught. Okay, fine. And then the tangent to the curve C, at the point x naught, y naught, z naught, I may call it r prime t naught. Is it clear to everybody? Right?
Yes.
Okay. So now what is going to happen? Say, suppose grade u naught and then r prime t naught. This is equal to 0, say. This is equal to 0. So that means what is going to happen? The tangent plan to the surface given by u1 equal to c1 at the point what? At the point x naught, y naught, z naught, right? So you are going to have a normal like this, isn't it? And that normal is perpendicular to this. Are you getting my point? Had this happened,
Yes, sir.
I'm just considering a potential scenario which is impossible. I'm going to tell you that. Okay. See, then similarly for the other surface also, if this happens, so then what is going to happen? As before, for the surface corresponding to this, what is going to happen? This vector is going to lie on the tangent plane of this surface at that particular point. That's it, isn't it? Right?
Yes, sir.
Okay. So in that case, what is going to happen? Irrespective of the existence of v prime, this vector, what? It is always perpendicular to both u1 and u2. Sorry, perpendicular to both grade u1 and grade u2. Is it okay? This product as a vector is always perpendicular to both grade u1 and grade u2. Right? Isn't it?
Yes, sir.
So that means if they have to be perpendicular to grade 1 and grade u2, they must be along the direction of r prime t naught, the tangent vector, isn't it? Right?
Yes, sir.
Right? But I have been given that u1 and u2 are two first integral, and of course first integrals, and they are functionally independent integrals of v bar, right? So that is why the direction of this vector is always in the direction of v bar, right? And we have been given that v bar is not a tangent to the curve at this point, right? So that is why at least one of them has to be non-zero. So geometrically, I'll tell you, this situation is like this. If I assume that at least this is not equal to 0, this dot product is not equal to 0, so then what I am going to have, say, suppose I consider a surface like this passing through, not passing through, where this point lies on the surface. So then what I'm going to get here, this is going to be grade u1 at x naught, y naught, z naught, and then you will see that this one is a vector lying on the tangent plane at that point to this surface u1 equal to c1, right? So the direction of all the tangents, direction of all the vectors lying in this in this plane, in the neighborhood of x naught, y naught, z naught, their direction is going to be different from the direction of r prime t naught. Is it okay, or it's getting too complicated? You tell me. If you have some difficulty, I'll still explain or re-explain. Because you need to understand the concept geometrically. See, let me tell you. Okay. Say, let me get back to grade u1 and grade u2. Okay. So, from the given conditions, grade u1 cross grade u2, it is always going to be in the direction of v bar. Okay, fine. And again, like if grade u1 dot a tangent vector to the curve c at the point x naught, y naught, z naught, if it has to be 0, then what is going to happen? That tangent vector is going to be perpendicular to grade u1. Okay. Also, you know that grade u1 and grade u2, their cross product is perpendicular to both grade U1 and grade U2, right? So that makes the cross product of grade U1 and grade U2 as a vector is a parallel vector to the tangent vector to the curve, which is impossible because we have been given that V is not a tangent to the curve C at that point. Whereas the cross product of grade U1 and grade 2 is along the direction of V, right? So that is why either du1 dt is not equal to 0 at t equal to t naught or du2 dt at t equal to t naught, either this is not equal to 0 or this one is not equal to 0. Is it clear now? Yes? Fine?
Yes.
Yeah, you please, I mean, see, the videos will be already there, my lecture video, don't worry about it. So, you go back home and again, open, Thor's book, and he has written them, but hasn't given all the explanation probably, okay? And get back to this, you'll be fine. Okay, so now, suppose we assume that this is not equal to 0. This is not equal to 0. So that guarantees me that I can eliminate t from these two. u1 equal to say small u1 x naught t, y naught t, j naught t, and u2 j naught t. Okay, so basically what is going to happen? I'll be able to find say t in terms of u from this equation. I'm going to plug that in here. I'm going to plug that in here, right? And that is going to give me something like this. You see your u2 minus f of u1 equal to 0. Where f is a C1 function for the variable u1t defined in the neighborhood of t naught belonging to I. Is it okay? Fine? Okay?
Yes, sir.
Right? So then what is going to happen? Your integral surface for corresponding to V in the neighborhood of x0, y0, z0, it is going to be given by simply this u2 your xyz minus f of u1 xyz equal to 0. So basically what you are going to get, I am going to get the integral surface as capital F xyz equal to 0, where your capital F xyz, this is nothing but your this u2 xyz minus f of u1 xyz. Any arbitrary function is going to do. Any arbitrary function small f is going to do. Okay. So in fact that completes part of the theorem, not the whole theorem. So now can you tell me? What is the guarantee? What is the guarantee that the curve C is going to lie, again, not the whole curve, only in a very small neighborhood of this point x0, y0, z0. What is the guarantee that it is going to lie on this surface given by this, or it is going to lie on this surface? What is the guarantee? What is the guarantee? see, remember, the guarantee has come from the origin of this expression. Origin of this expression. Origin of this expression is what? This, isn't it? Right? Okay? Fine? Isn't it? And over there, those were capital U1 and capital U2. Those were functions of small t in the neighborhood of t naught. Right? Isn't it? So obviously, in that neighborhood, neighborhood, what I have defined the what curve through that parameterization. Okay, so that is why the curve C must lie on the surface given by this. Okay, see now I mean it may not be that clear to you, but I'll take one example and then you got to believe me that this really happens. Okay, this really happens. Okay, so again I have just proved that there is an integral surface. There is an integral surface in the neighborhood of that point x naught, y naught, z naught, where I mean the vector v is not a tangent. Okay, but what I haven't done here is that it is unique. It is unique. Okay, so the uniqueness, you please go through Thor's book. It is given there. Okay, uniqueness part that I am not going to do. But the thing is that we have been able to find an integral surface. Basically, what we want to construct, right, an integral surface containing that curve. That's it. So that we have been successful. You should be happy about that. Okay. So I will do two exercises. One is I already worked out in the book, and the second one is an exercise in that book. And okay, so basically, how do you find that integral surface? It eventually boils down to finding out two first integrals of v. Okay, fine, and then eliminating t from those two expressions. Okay, so let me. Okay, so find an integral surface corresponding to the vector say v xyz containing the curve C given by y equal to x plus 1, z equal to x square, x greater than 0. Okay, so now the very first thing you'll have to do is parametrizing the curve C. Yes, can you parameterize it? Yes. If you parameterize the curve C, what that is going to be? RT, C is given by say RT. What will be the components? X is T plus 1 T squared. Okay, fine. So now what this is going to give you, it is also going to give you how V looks like for of course here. Okay, so how V looks like in terms of T. Okay, for those points. Okay, I'll come back to that. Fine? Okay? Is it okay with everybody? Right? So this is nothing but the tangent vector at any point for t greater than 0. Okay? So now if I take the same points if I take the same points and parameterize the vector v, so then your v is going to be what? V is simply going to be this same thing. V is simply RT. And remember, V is not always going to be RT, because the way it has been given, that is why. Okay, so V is again 1 t plus 1 t squared. Clear? Yes? I am getting it from here, but you shouldn't think that it is always going to be like that. That is what my point is. I'm going to take another one later on. Okay, so what does these two say? What does these two say? These two say that nowhere like V is going to be tangent to this curve, because you can see that they are completely different. Isn't it? These two are not parallel at all for t greater than 0. Clear?
Yes, sir.
Right? So now we can find out this methodology. We can adopt the methodology in this theorem to find out an integral curve for this case. Okay. So now, obviously, as I have told you, the next thing is to find out two first integrals of v. So you know that, I mean, I am going to find it from okay. So this is obviously you can take u1 x y j. This is equal to x by y, and u2. Is it okay? Simply finding out. Take pair. I mean, I have taken first two and then first and third ratios. Is it okay?
Yes, sir.
Fine. So now let us see what happens. Now, so that means capital U1, that is going to be x was equal to t, y is t plus 1, right? Okay. And U2, j is t square, this is t, this is equal to this, right? So then if I eliminate t from these two expressions, so then that is going to give me what? U1 equal to U2 1 plus U2, right? So this is going to give you U1 1 plus U2 minus U2 equal to 0, right? So therefore the required integral surface is given by simply just a minute. Just a minute. Let me see. Earlier I told you that see U2 f u1 equal to 0. I told you that this f is an arbitrary function. So now you can see that it is not arbitrary. It will come from what? This expression itself, isn't it? Are you getting my point? Are you getting my point?
Yes, sir.
Right? Right? So that will come from the elimination of t from one of them. Either whether you are going to take u1 minus f u2 equal to 0 or u2 minus f u1 equal to 0, that will come from the choice of elimination. Okay? Right? So that means the function capital F that you are going to define, that is going to be fixed. Okay, and that is going to give you the uniqueness of that surface. Okay, fine. So that means the therefore the given surface is going to be what? You simply replace capital U by small u. So what we are going to get? That is x by y, then 1 plus u2 equal to j by x, and z by x is equal to 0. Therefore we require integral surface is this. So I'll just okay. Of course, you have to define this surface for x greater than 0, y greater than 0, or x less than 0, y less than 0 also you can do. Now, okay. Now, one thing. How do you know that the how do you know that the curve C lies on this surface? How do you know that? What was the parametric equation of that curve C? I mean, RT was this, isn't it? Yes? Yes. So if you plug in the values corresponding to x and x, y, z here, then you will see x by y, so t by t plus 1 plus t squared t plus 1, z by x is t. So this is going to give me t into 1 plus t. Okay, 1 plus t I can write minus t. So, sorry, t minus t, this is equal to 0. Are you convinced now? Yes, this theorem works. Isn't it?
Yeah.
Right. Let me take another quick example because I'm going to use the same vector later on. So this is another exercise. This is another exercise. So V is given by your 1 1j 1 1j, and C they have already given the parameterization x equal to t, y equal to 0, and z equal to sin t. Z equal to sin t, and of course t they have defined in the whole real line. T they have defined the whole real line. Okay, so verification part I will be leaving for you. So at least here, I mean, V is different from C. Okay, so here the C is given by this vector RT 0 sin t, right? So R prime t, this is cos t. Is it okay? Fine. So now, if you compare this R prime t with the vector V, obviously they're not scalar multiple of each other, so they cannot be parallel, right? Isn't it? So I mean, V cannot be tangent to the curve at any point. Clear? Yes, right? So now if I look at if I seek the first integral, so dx by 1, dy by 1, dz by j, right? So obviously from these two I can get u1 xyz equal to x by y? No, x minus y, right? Right? X minus y. And if I use the first and third, so this is going to give me x equal to ln j plus ln c, something like that. So I can get j by e to the power x. Is it okay? Is it okay from the first and third? Isn't it? Right? So j by e to the power x, so e to the power minus x into j. Fine? Okay? So now what you do, you plug in the values of t here. So that means capital U1, that is t minus 0, right? And capital U2, this is going to give you e to the power minus t sin t, right? E to the power minus t sin t. So this implies what? Your u2 equal to e to the power minus u1 sin u1. Is it okay? Right? So that means the required integral surface will be given by this minus this equal to 0. So u2 was what? u2 was e to the power minus x j. So this is equal to e to the power minus x minus y sin x minus y. Okay, that's it. Or what you can do, if you want to write it as an explicitly as a function of this, what this is going to give you, e to the power y, right? Yeah, e to the power y sin x minus y. So this is the required integral surface. Is it okay? Fine. Okay, and you can check. You can check that it is satisfying. It is satisfying for all the points lying on the curve C. You can easily check that, because see, z equal to sin t. Sin t is y0. This is 1. Again y0 sin t. X is t. Is it okay?
Yes, sir.
Fine. Okay. So
Yes, sir.
thanks. So now let me come to the other part, the second case.
Excuse me.
Yeah. Yeah. Go on.
Sir, in that auxiliary question, that dx by p is equal to dy by q is equal to, sir, we can take any combination. So
Yes. Any combination is going to work. Yes.
so u1 and u2 are going to be different.
Yes.
They are going to be different.
Yeah.
So how can we assure that it will be unique?
Unique. It will be unique. No, whatever combination you take, that has to work for the values of t in the neighborhood of t naught, right? And the elimination part is going to come from that. Elimination is going to come from that only. Okay, and that is going to guarantee you the uniqueness. You can check. You can take some other way also. You can take some other way also. Okay, fine. And you please go through that paragraph that has been written in Thor book about this uniqueness. Okay, fine. You please check at home also by trying other integrals. And again, remember, whatever first integrals you take, they have to be functionally independent. They have to be functionally independent. Just a minute. So, do you recall the case 2? What happened in case 2? Like when we considered that curve, C in space.
When v is tangent at every point.
Yeah, so that curve itself is an integral curve. So, the proof of the next theorem, I am just going to explain it. You write down the proof yourself. I am going to explain it and in in the book that I'm following, they are simply, giving, 3-line proof, I guess. But I'm going to explain you all this stuff. Don't worry about it. Okay. Just a minute. Okay. So suppose is tangent to C every point here. There is a twist, huh? In the neighborhood of course, all the assumptions, not really assumptions, all the information, it is valid corresponding to that parameterization. Please remember that. Okay, fine. X naught, Y naught, Z naught, of course. Belonging to C. So here basically what they're saying, let me just explain this statement. Say suppose this is my curve C, okay, and suppose this is the point x naught, y naught, z naught. So what they have done, they have taken a small neighborhood of this, okay, right? And at each point is this neighborhood, your v is a tangent. That's it. Is it okay? This is the meaning of this. X naught, y naught belonging to C. Okay. So the next line, it is interesting. I'll tell you. Then in some neighborhood, see, the earlier neighborhood we defined it as omega naught. Is it okay? Right? You remember earlier in the previous theorem we defined the neighborhood of x naught, y naught, z naught as omega naught. Fine. Now you see what it is. In some neighborhood, omega 1, which is a proper subset of omega naught of say x naught, y naught, z naught, x naught, y naught, z naught. There are infinitely many integral surfaces of V containing the portion of C lying in omega 1. Yeah, can you tell me about this omega 1? What is so specific about that omega 1? Can you tell me? Yes? Why now omega 1? Earlier we had omega naught. That should have been enough. In fact, now still it is enough. But why rope in that omega 1? It is just to indicate you something. So can you tell me what it is indicating? Yes? What it is indicating? We are considering even a smaller neighborhood. Are you getting my point? We are considering even a smaller neighborhood. Okay, so now you may be thinking why I need even a smaller neighborhood. I'll give you the explanation. In fact, this statement itself, it guarantees you an integral surface. I'll tell you. Okay, fine. So proof. Proof. So now what I'm going to do, again we are going to consider small u1 and small u2, okay, as two functionally independent first integrals of v in the neighborhood, say omega 1. Of course, this is also a neighborhood of x0, y0, z0. x0, y0, z0. Okay, say now you should appreciate the difference between this theorem and the very previous theorem that we did. This theorem tells you is that v is tangent to every point of C in the neighborhood of x0, y0, z0, right? So what does that make? That makes what? D portion of C in the neighborhood of x0, y0, z0 an integral curve of V. Is it clear to everybody?
Yes.
Right? Okay, fine. That is our first information. Say I am unfolding the information bit by bit, but I think now you should have some idea about how to go about this proof. And proof is simply going to be, some statement. Okay, fine. So then what is going to happen? Okay, from this information, can you make some statement from here? And yes? Yes? This one, does it give you some information? Obviously that vector, right? That vector, what? It is parallel to V bar, right? V bar, isn't it? And again, we have been given that V bar is tangent to all the tangent in a whole, tangent in the neighborhood omega 1 of C, omega 1 of x0, y0, z0 on that curve, right? So basically, what does that tell you? So obviously, in the neighborhood of that point x0, y0, z0, what happens? Like this vector is along the direction of r prime t naught, isn't it? Yes?
Yes.
Right? And again, this vector I can consider to be coming out of the cross product of the normals drawn at the point x0, y0, z0 to some level surface given by these two equations, and of course in that neighborhood, in that very small neighborhood. Is it okay? Right? Okay? Fine? Isn't it? So,
Yes.
so that means if I want to consider the level surfaces corresponding to the first integrals u1 and u2 in the neighborhood of x0, y0, z0, so then what must happen? Like what I'm going to get, these constants c1 and c2, that will be given to me by this, and c2 will be given by this. Fine? C2 will be given by this. Isn't it?
Yes, sir.
Huh? So now, okay, forget about proving something. I'm going to rope in your final final integral surface. But if you geometrically imagine this situation, okay, let me try to draw it. I don't know. Whether I'll be able to do it or not. Say, suppose this is your this is x naught, y naught, z naught. Okay. So what I am going to do as before now. Okay, say suppose I am considering this, so then suppose this is my u2, and of course it is going to be, this is going to be some non-zero scalar, right? It is going to be along the tangent to that curve, this, because that is an integral curve. Is it okay? Fine. So now, say if you use the continuity of those functions, x, y, z, u1 and u2, right? So then what is going to happen? In the neighborhood of that point, what you are going to get? Like this surface, you are going to have a common surface, isn't it? The intersection of the surfaces u1 and u2, right? From there, instead of the intersection being the curve C in that particular neighborhood, you should get what? A surface, isn't it? Are you getting my point? Just simply think about the continuity of those surfaces in the neighborhood of that point. Because if grade 1 u1 cross grade 1 u2, right, that has to be along the direction tangent to the curve at that point. So can you visualize a very small surface, right, which is going to be common to both u1 equal to c1 and u2 equal to c2? Yes? Right?
Yes, sir.
Right? So now what is happening? They have been given by this, and they are coming from this. Okay. So then what is going to happen? If you define a new function, this f of u1, u2, in such a way that this is equal to 0, this is equal to 0. So then f of u1 and u2 equal to 0 is going to give you an integral surface of V in the neighborhood of x naught, y naught, z naught. And here again, remember, here the choice is arbitrary. Okay, you can take any choice. Is it okay? Fine. Here, this condition has to be satisfied. This condition has to be satisfied. Because that continuity concept that I was telling you, that corresponds to these two surfaces. Okay. When you are going to choose these u1 and u2, you got to choose them in such a way that there is some, level surface U1 equal to C1 and U2 equal to C2, where C1 and C2 are given by the value of U1 and U2 at the point x0, y0, z0, and that is, this expression is going to guarantee you an integral surface. And since your choice of capital F is arbitrary, you can have infinite number of integral surfaces. Okay? So now let me try to work out another example, so that again, you are convinced that whatever I have told you is correct. And again, please revise it again at home. Okay? Because see, the geometric part probably you have come across them for the very first time. So it will take some time for them to, seep in your brain. Okay. Okay, I'm going to take the same vector. This is again finding out the integral surface corresponding to this vector field 1 j 1 j, and now the curve is different. The curve is different. It is given by x equal to t, y equal to 1 plus t, but j is e to the power t, and now this is the range of t. Okay, so you have to find out an integral surface for this vector field where this curve lies. Okay, fine. So from this parameterization, you can see that RT is t 1 plus t e to the power t. Okay, so R prime t is 1 e to the power t. Is it okay? Fine. And if you write V for those points lying on that curve, isn't it? So then you can see that they are the same. Is it okay? Isn't it? Are you getting my point?
Yes, sir.
Yes. So that means, what? V is everywhere tangent to this curve. To this curve, C parameterization given by this. Okay. So now, then what we are going to do as before? We got, say, for this one. What's it? 1 1 j. Okay. U1, that was what? X by y, and U2 we found out e to the power minus x j, right? J. Is it okay? Fine. So now you check. Now capital U1, that is going to be given by x by y, and x is what? Just a minute. Is it 1 1? Just a minute. Yeah. Just a minute, right? E1, yes. 1 1 j.
E1 will be x minus y.
Oh, that was x minus y. Sorry. That was x minus y. Yes, this is not the first vector. Okay. So now you will see that U1 is t minus 1 plus t. This is equal to minus 1. Okay, fine. And then U2 equal to e to the power minus t, e to the power t. This is 1. isn't it? See, so basically, see, this theorem was telling you that in the neighborhood of some fixed point, right? You will be finding out capital U1 and capital U2 to be constants. Are you getting my point? Right? But here, throughout the whole interval, 0 to infinity, you are getting them as constants. Okay. So then, what is going to happen? Although I didn't mention capital U1 and capital U2 in that theorem when I proved it, but they are nothing but see what. Just a minute. You remember. I was taking like this. Okay, that C1. I was taking something like this. If okay, although in the proof I didn't mention it, it was something like this. Is it okay? Fine. But here what is happening? Instead of some fixed T naught, I am getting these constants for all t belonging to that interval. Now, are you getting the point? Right? Okay. So that means I can take any this zero as my integral surface, subject to the condition that f of -1 this is equal to 0. So can you give me a combination like this? Can you give me a function? Capital F in such a way that this f of -1 becomes 0? Yes?
Just simply their addition.
Yes. Isn't it? Simply the addition. Or simply what you can do, -1 squared -1 equal to 0. You can make any combination, right? Isn't it? So, like if I take this as f of u1 u2, this is equal to say simply u1 plus u2, right? So then you can see that that is going to give me the required surface integral because it satisfies this equation. Is it okay? Is it okay with everybody? Right? So that is why I can take x minus y plus e to the power minus x j equal to 0 to be my integral surface. Corresponding to the vector field v bar. Is it okay? Fine?
Yes.
Right? So, and here see, you have infinite number of choice such that this happens. So, that will bring you infinite number of integral surfaces. Okay? Fine. How much time do I have? Okay, anyway. So, now you may be thinking that, like say, I'm kind of deviating away from the syllabus. Don't worry, I'm not. What I'm doing, like say last time when I taught this particular portion, I didn't teach him this way. I specifically considered, those portions from the syllabus. But now I have seen that, if your concepts regarding the geometry, it is clear, then you'll be able to solve anything. And that is what exactly the next chapter tomorrow. What I'm going to do, I'm going to start first order PDEs. No, first order PDEs. Okay, first order PDEs. Oh. And the authors, they have exactly described that the theory that we have developed till now, that is going to be very helpful in understanding this. And you will see that many of the stuff, now I am not going to prove any theorems. I am not going to prove any theorem because all the theorems required to tackle first order PDEs you already know. Only some slight modifications I'll have to do. Okay, fine. And again, I think I'm going to hold your next quiz on Saturday, but the syllabus is going to be only after mid-sem and the ODE part. The ODE part after mid-sem. So basically, it is going to deal with all those critical points, stability, all those stuff. Okay. So I'll definitely I'm going to send you an email regarding that. Okay.